Hello everyone, this is Dr. Aeronautics. So the question that I might get asked nowadays is, why am I called Dr. Aeronautics? Because I've been taking a lot of train trips on YouTube. Well, when I originally set up the YouTube channel, I set it up to be a host of adventures in spaceflight simulators that I would record and upload. And I have accomplished enough of my secondary objectives to say, you know what, it's time that I finally go to that primary objective. So as a result, today I will be showing you how I develop, plan, configure, execute, and archive a simulated space mission. Okay, here is the outline for basically what is going to happen in this series. I am right now planning approximately 7 episodes in order to encompass all of these planning stages and flight, the entire mission, cradle to grave as we call it. So the very first thing we're going to do is we're going to find and select a destination and a departure base that we're going to use. You know, where do we want to go in space? What do we want to do? Which is the itinerary. So we will be saying, okay, this happens in a certain order. Maybe you're going to fly to a planet and then visit and land on a moon, set up a base, and then maybe pack it up and move it somewhere else. That's all in the itinerary. Then I'm going to show something called the tech levels and ways to fly, because in spaceflight simulators, you can go outside of what is normally possible nowadays. And I'm actually going to do this this time and go out into the future into something that you could see maybe in 100 years or so. Then we're going to select a particular way to fly based on that technological age and choose a mission planning software that will allow us to plan the mission with very, very accurate detail. Then we're going to take a look at our itinerary and figure out which vessel matches the flight that we're going to do. We're going to select a vessel. If you wanted to go really crazy, you could design one. That would especially happen in the earlier stages. Definitely 21st century missions, which is why I opt to do the 22nd century missions, so that we can use a one-size-fits-all spacecraft. Then we're going to walk through updating and inspecting the checklists, and then we're going to move on to actually doing what they call product exports. And product exports are basically everything that we need to fly. There's a spreadsheet that I'm going to show you guys, calculators that are required, a fuel budgeting spreadsheet that we'll use to determine what our fuel situation is, an oxygen tracking spreadsheet. These are all things that even in the professional world are referred to as products. And in the professional world of spaceflight, we store all of these products in a conglomerate just declared a database. And this database contains everything that you need to fly the spacecraft. Then, because we're in a spaceflight simulator, we're going to be setting up a scenario editor, initial settings, add-on modules, and optimizing it so that only what's required for the mission is going. In real life, spaceflight simulators are actually part of the mission, but they're a backstage, because the idea of a spaceflight simulator is you want to know, okay, if I do XYZ to the simulator, what happens to the spacecraft in real life? Now, unfortunately, because I don't have access to a real-life spacecraft from the 22nd century, and all of the required permissions from all the governments and IAU, and I guess IAU doesn't have a say in that matter, but because I don't have access to all of that, the spaceflight simulator is going to be treated like it's the real thing. And then comes the fun. Why do we do this? To fly. So we're going to fly the outbound leg in what I believe one episode, and then we're going to do everything that we're going to do at the destination in one episode, and then we're going to fly the inbound leg in a final episode. And when we're all done, we do what's called a debrief and archival. Basically, what did we learn from the mission? And it's not that boring science fair or science class lab paper where it's like, oh, I conclude that this, and that. No, what we're going to do is we're going to basically look at a fuel spreadsheet and say, okay, how close were we? How accurate were we? That's like our game score. How close were we to being perfect? Then we're going to look at how what we planned compares to what we flew, and then look at some really awesome pictures and data. We can actually record atmospheric data or anything else that we learn, and just put that all in one piece and just take a look at it and be like, wow, we actually accomplished something. So that's basically what's going to happen in this series. Here is the fuel tracking graph of a flight that I flew last year to Uranus. And the great thing this time is I finally installed a secondary Bandicam license on my library computer. So instead of saying, oh yeah, planning is happening off screen, I'm inputting my numbers, you're actually going to see it this time, which is great. So now hopefully things will be a lot more logical and practical. Anyway, so what you're looking at right now, the blue line is how much fuel I put in the tank and how much fuel remains in the tank throughout the journey as we start to use it up. And then the red line that you see going across is the amount that I planned would actually be needed in order to make it back to the base with zero fuel left over. So I did factor in about 5% contingency. So then what I did is, okay, as part of the archiving, that I talked about and said, okay, we're going to compare the actual with the initial. That green performance line, what I did is I said, okay, if I took off with exactly the amount of fuel that I planned that I would need, which showed somewhere around 3,250 kilograms, we're using 22nd century technology. So getting to Uranus and back on 3,250 kilograms of fuel is well beyond anything that we could even see happening now. But if you follow the green line, it does go a little bit below the red line, but not much. I actually calculated it out, and we used 1.1% more than what we planned. So we had 5% in reserve, and we only used 1.1% of that reserve. And when I saw that, that just gave me a very, very huge, oh my gosh, I actually accomplished something feeling. Like all that hard work paid off. To be able to plan your flight to have a fuel contingency reserve accurate to 1.1% is amazing. In fact, I think NASA even budgets more contingency mass into their propulsion tanks. So that makes me really happy when I see that. And that's what we're going to basically aim to reconstruct in where we're going next, and say, okay, I need 3,000 kilograms. I'm going to put 3,100 in the tank, and we'll see how close we come. That's going to be really, really, really fun. All right, this is the spreadsheet that I actually used for mission planning last time I flew to Uranus. And this contains everything planned about the mission, some important information about vessels that were candidate for this mission, and then I've got my crazy calculators that I've always talked about, and say, okay, I'm putting in some information now, and I'm getting out a magical value, well, the information goes in the green area and it comes out the blue area. So you'll get to see that in work, and we're going to use this both in the planning and in the execution of the mission. So now we can actually go over to the mission information table, or the MIT as I'm calling it, and right away you'll see in the upper right, here's the actual graph that was used during the mission while it was taking place. So when I was 19 AUs away from the Earth, I was looking and saying, okay, I've got 1355 left in the tank. Survey says I need 1016 to get home. And that continued all the way to the end, and the final fuel level left in the tank was 292 kilograms. That's what we got home with. So you can see here's some information about where I went. I didn't just go to Uranus, I also went to Umbriel and Oberon using a Delta Glider 4, and I did this out of Wallops Flight Facility. So then I ordered everything. This is the itinerary. I have a launch mass here, which is calculated, and then a timeline, how long the entire flight took. This is the most unrealistic thing of all. 34 1/3 years. Human lifespans are going to have to get a lot longer before we try to plan or try to fly a mission like this that's this long. So that's a little bit tricky. And this massive table here is all of the maneuvers, all of the propulsive maneuvers, the engine firing, how much fuel was in the tank before, what the mass of the ship was, the velocity at the beginning of the burn, the velocity at the end of the burn, the expected needed delta V, and the expected needed delta V to, or sorry, the expected fuel needed to complete all future burns. And that's what I use as the red line to track. If my fuel before the burn touches this, then I'm like, okay, the flight's aborted. So let's see, we went to Uranus, did not get a chance to go to Umbriel yet. Sorry, we're going home. We're out of fuel. That's what I'm gonna do. So anyway, it did succeed, and you can see throughout the mission things tick down. And then at the very end, I have a number of parameters for the mission, like a safety margin. I actually blanketed 10%, thinking that I couldn't get close enough to 1.1%, and it ended up being about 10 times larger than was needed. So we're going to make it a little bit smaller this time, but not anywhere near as small as what we did last time. Or sorry, other way around. Not anywhere near 1.1% accuracy. That's really dangerous. Okay, continuing down, I also have some flight notes. So basically things that I realized, hey, this is important to the mission. I should write this down for the future. I wrote it down here. Then we have the timetable, basically what is expected to happen when, how many orbits we're planning to make. This was all used to calculate the duration of the mission. And then we have some loadout information. When we took off, how much fuel we loaded, what our engine power was, the time that we expected the flight to occur, and just so that I can visibly check, and yes, we're not going to run out of oxygen. You look at this O2 years on board, which is the tank plus the cargo bay. What I'm carrying, the number of passengers, and the amount of fuel that we loaded into the RCS system. And then we have the scratch zone, which basically just shows real-time calculations that I just did offhand. This is just really messy, what would be the equivalent of scratch paper on like a math exam. And then at the very end, I probably should have made this bold. Here are the final numbers. Final vessel mass, the amount of RCS fuel left over. Or sorry, that's fuel. This is RCS fuel. payload mass. So we basically took all the payload home, I think. Or no, we didn't, because we put some extra oxygen in the cargo bay and consumed that. So that decreased. Dry and wet mass of the ship and actual long-term error. Only 62 kilograms of fuel after expending about 3,000. Yeah, after expending about 3,000 kilograms, we were 62 kilograms in error. So basically, if I used my RCS fuel as my contingency, which I'm going to do this time, we'll still have leftovers. So what I'm going to do is basically factor in no extra fuel, and if we need the contingency, it's in the RCS tank, and we take it from the RCS tank. So I think this factored out to 98.1. All right, I want to be very clear about this. When I said 1.1%, sorry, it's 1.9%. I did not hit 1.1%. We can try this time, though. So that's what we're going to plan. Okay, so we already covered the debrief. That was basically at the very bottom of the spreadsheet. But then I mentioned an archive, right? We take pictures and stuff so that you can see what happens. So I also saved all of the quick saves. It took 119 quick saves. But this enables me to recreate any phase of the mission at any time in the spaceflight simulator to relive it. So here's the very first picture. We're on the ground at Wallop's flight facility. Here's some fuel and cargo. This is basically all the cargo that we loaded up into the cargo bay, right? Okay, and then we took off, flew over the East Coast, got into space. This looks interesting. Okay, so this is us after arriving at planet Uranus. And one of these times I actually went low and sampled the atmosphere. I think I got a picture of some of the cloud tops. Okay, I found it. It's this one. You can see a little bit of cloud top detail in there. So we're actually close enough to Uranus that it's not this crazy green ball. And you can actually see a haze layer there. So the haze is what starts up here. And then you actually can see through the cloud tops, the methane clouds down to the ammonia clouds there. And you can see we actually significantly did go into the atmosphere. 0.5 pascals, the nose heated up to 438 degrees Celsius, and the outside air temperature would have been somewhere around, I think it's minus 200 Celsius. Well, we're probably in the thermosphere. But anyway, it should be very, very cold, and the nose is very hot. So that shows you how deep we got into the atmosphere. There's a nice view of the rings. And then I had mentioned that we went to Umbriel, right? So here's everything unpacked in Umbriel. And then at some point I set up my base. So here's the inside of the base. Here's the outside of the base. Okay, so then we flew to Oberon. And we landed and set up a base there. And then we left the Uranian system and returned home in 2149 and landed at the exact same location that we took off and unpacked everything again. Okay, so now we are beginning the very first step of planning our new mission. As of now, I have not selected a destination. I love all of the planets and moons in the solar system so much that I can't decide between them, and I have to let fate and orbital mechanics dictate where I'm going to go. So even as of yet, I still have no idea where we are flying. So, picking a departure base. The question you want to ask yourself is, what motive do you want to use for choosing your base? Is it near home? Is it your favorite place to visit? Maybe it's most realistic, or even some combination of them all. For me, I use a combination of two. I go with Wallops Island because it's a real NASA launch facility in the mid-Atlantic region.
3, 2, 1, roll.
Now, how about your motive in picking a destination? Is it your favorite planet or moon? Random? Maybe you like a challenge? Again, I'm going to use a semi-random selection process. So I'm going to choose the planet that is most aligned with Earth for a departure on the current calendar date in question. I am recording this on Sunday, September 26th at 1800 UTC. So, I'm going to use that date to determine where we're going to fly. Okay, I call this spreadsheet the sneak peek clock. The time a planet is at its highest in your sky actually determines how possible or impossible it is to make a 0G or home-in flight, which is the kind of flight we're going to do there. And the time varies for the planet. So, for example, for Mercury, I should mention that where you see time of peak, that's in hours local time. So at 7 a.m., 7:30, you can fly to Mercury. In the evening, about 8 o'clock, you fly to Venus. Then very early in the morning, 5 a.m., if Mars is at its highest peak at 5 a.m., you can fly to Mars. 6 a.m., if it's there, to Jupiter. 7 a.m. Saturn. 7:30 to Uranus. And 8 a.m. to Neptune. This isn't when you take off, but it's the time of year. So if it's 7:30 a.m., or sorry, 8 a.m., and you look up in the sky, and Neptune is high in the sky at 7:30 a.m., it means that it's the right month to travel to Neptune. If, however, Neptune was high in the sky at 8 p.m., then I would say, sorry, you're going to have to wait 6 months. And that's just the way it is. Now, column G, I have this thing called the Viking hour. I'm a little bit obsessed with Vikings. So I actually have the hour that they would have named when you see it. And interestingly enough, everything with the exception of Venus occurs in the mid-morning hour, which is basically sunrise-ish, with the exception of Venus, which is mid-evening. Okay, as mentioned twice before, I have intentionally not paid attention to the positioning of the planets, so we have no idea where we're going to fly. We're going to do that right now. Alright, our position is intentionally set to Wallops Flight Facility. So now we're going to go to Sky, and I like to choose Horizon to Zenith. And we'll just start checking the planets. So, let's see, that's the local time. So we're going to go back to 7:30 a.m. Okay? And I want to look for a planet that's high in the sky, Mercury, and it's nowhere to be seen. If it's here, it's going to occur near the sun, because Mercury is very close to the sun, and we're further away from the sun than Mercury, so it's always going to appear near the sun. So it's not Mercury. And by the way, I know I said I can't choose between anything. What I can choose, however, is a major planet from a minor one. So we're going to go with a major planet. Whatever we pick, it's going to be a major. And then let's see, we're gonna go check Venus now. So we want to go forward to 2045, and in the south. Oh, let's see, Venus isn't there. So I guess we're going to scratch Venus too. Then we'll check 0500 for Mars. Mars should be high in the south, and it is not. So scratch Mars. Then we can check 0630 for Jupiter, and it's not there. So scratch that. Then we'll check 0700 for Saturn. It is not present. 0730. We might have a match for Uranus. And then 0800 for Neptune. And Neptune is nowhere to be seen. So we might be going back to Uranus. We're going to take a look at Transx now and confirm that Uranus is the place to go.
Okay, here we are in A simulator at Wallops Island. We got the current date. So now what I'm going to do is I'm going to go to Transx. I'm going to escape Earth. I'm going to go to Uranus, and now I'm going to go back and just start adding prograde velocity, and we're going to see how close we get. We definitely don't want to go that far. Start adjusting this a little bit more closely here. Yeah, that's looking really good. I think 50 Gs would even give us an intercept. Yes, it does. Okay, let me just roll it out by doing the other planets, just to confirm. Okay, I dug a little deeper, and here's the deal. So the timing that I was giving is for a perfect scenario, and Uranus actually wasn't a perfect scenario. It was a off-nominal scenario, and it just so happens that also off-nominal are Saturn, Jupiter, and Venus. So I didn't want to go to Uranus again. I probably should have excluded that, because I'm trying to get more experience and go in the same place twice. Although Uranus does have extra moons, I was hoping for someplace a little bit more exciting. So we're not going to go there, and we have some extra options. Now we've also got access to Venus, but again, it's that whole thing of there's not enough to do at Venus, because Venus has no moons, and I don't have anything that we could really go to the surface in. So there's not really much planning that can be done. So we're going to skip Venus and skip Uranus, which means it's a battle of the giants, Jupiter versus Saturn. And the winner is Saturn. I determined this by basically comparing the velocity needed for this flight compared with an ideal situation. With Jupiter, we would need 9.966 kilometers per second out of a typical 8.963 kilometers per second, for a ratio of 1.111 times the normal ideal delta V. And then for Saturn, we have 11.07 of a normal of 10.33 for a ratio to the perfect of 1.071. So, Saturn is the most aligned of Jupiter and Saturn. So, the destination will be Saturn.
Okay, so it is now time to start writing things down. So I copied a template called Generic Flight, and this will be called Orbiter Saturn Expedition, and the date 09/26/21. Open it up, and here we go. This is got everything that we need to start with. So we'll put the ultimate destination in, Saturn. Then we're going to pick some accessory destinations next. We don't know our vehicle yet, but we know our home base. Wallops Flight Facility. And I'm going to have to... I've got some notes in here just for me to read through and understand how this spreadsheet works. I'm going to clear it out. Okay, all that stuff has been cleared out now, and it's time to ask the question, what do we want to visit at the destination? You want to look at the whole system. This is a list of everything that I can think of that I would ever want to visit. Some things don't exist. Bases, I'm going to be doing this from a exploratory standpoint, so there won't be any bases in the Saturn system. It's just going to be as it is today, completely empty. No space stations there either, although we might make use of a mothership, depending on the technology choices that I'm going to be making in a couple minutes. So here we go. We want to list and evaluate all destinations available to the most detailed as possible. I don't have any interest in going to the Trojan asteroids of Saturn. I'm more interested about going to Saturn itself, because if you go to the Trojans, it's so difficult to go to Saturn that you might as well make a separate mission at that point. So moons. When it comes to Saturn, there's a couple moons that have extreme interest. Enceladus, because it has what many people think a undersea, or not undersea, an underground ocean, and it's covered by snow. And it shoots geysers of liquid water, and in some places it's blue. So we're going to visit Enceladus. And then, let's see, other moons to visit. We'll want to definitely visit Titan. Titan is basically the most interesting moon in the solar system, tied with Europa. And Titan is believed to have an underground ocean as well. But it has a surface lake, actually lakes of liquid methane. And it has streams and rivers and rain. And an atmosphere that's actually thicker than the Earth's. We can fly in Titan if we take along a spacecraft that has wings. So we're definitely going to Titan. Other moons of interest, I really like Iapetus because it looks like the yin-yang symbol. It's got some really interesting material on its leading, I think it's the leading hemisphere. One half is very, very bright like snow, and the other half is very, very dark like asphalt. So we're going to pick Iapetus. Then we got the rings. So what we're going to do is we're going to go through a ring gap on Saturn. So let's just put Saturn ring. And I'm going to leave a blank because we want to go between two rings. We definitely don't want to go through them. That's going to destroy the ship. The next thing is the atmosphere. Saturn has a very thick atmosphere. We'll be able to land on Titan. Saturn has a very thick atmosphere, so we can also add a Saturn atmospheric sampling. Then we've got cloud decks. I'm not going to fly in something from far future 500 or 1,000 years, so we're not going to be able to reach the Saturn cloud decks. That's out of reach using the technology that I want to do. We can at least observe them, though. And then we've got biomes. This is directly relevant to Titan, Iapetus. Well, no, just Titan. The biome that I want to visit on Titan is the lakes. And then next we're going to look into landmarks. On Iapetus, I want to see the dark surface. On Enceladus, I want to see a blue crack. These are areas that we'll actually see when we get there. Maybe even in the planning. There's no bases and there's no space stations. So I think we have all of the information that we need. We're going to start putting these locations into our spreadsheet. Okay. We need to order the locations that we're going to visit first. You want to order locations based on minimizing the need to retrace paths in space. And so, what do I mean by retracing paths in space? I mean what you could see on a delta V map. This is a delta V map of the solar system, and I'm very happy to see that it is colored black, so it works when you are flying in space. It's a lot easier on the eyes. So what I mean is, I don't want to come down to Saturn, dip into the atmosphere, and then say we're going to go up to Iapetus, and here's Iapetus, and then we're going to go down to Enceladus and visit here, and then we're going to go up to Titan. That's bad, because what we've done is we've gone back and forth over all these segments, and every time you see a brown number there, that means that we're expending fuel. So we only want to go once. That means we come into the system, visit Iapetus, then Titan, then Enceladus, then Saturn itself, or come shooting through the system, go straight down to Saturn, and then work your way up to Enceladus, and then Titan, and then Iapetus, and then be on our way. So, what we want to do in our case is go down to Saturn first. And the reason that I do that is because you're furthest from Earth, right? You've got all this weight, all these numbers on you of delta V that you have to expend, and you want to get that on top of you earlier in the mission so that there's less things that can go wrong, right? Because you're doing the worst of it first. We're getting into the most dangerous place, the cloud top, well, not cloud tops, the haze layers of Saturn. Okay, and then we're out of low orbit. Then we're on Enceladus, that's a little bit higher, and then we're going to move to Titan, that's a little bit higher, and then Iapetus, we're just a escape away back to Earth. So that's why I'm going to do it that way. Knowing this information now, we're going to begin putting it in to the accessory destinations. So we actually want to put some Saturn ring in, which we're going to figure that out. And then from there, the next out will be Enceladus. And then we're actually going to have to add some accessory destinations here. After Enceladus, we want to visit Titan. Add another one. We want to visit Iapetus. And then from there, that covers everything. The next thing that we need to ask now is, what do we want to do at the destinations and for how long? What's the space environment like? And we want to note that for selecting a vessel later on. We want to organize the answers to the questions into what becomes the itinerary. Okay, so I've thought about it, and basically what we're going to do here is create our phases. So what do we want to do at the destinations for how long? Well, first of all, there's a phase that goes Earth to Saturn. Then we're going to do a phase that says Saturn atmospheric sample. And then we're going to assume that we're in low Saturnian orbit, or LSO. So we're going to do LSO two rings. And now we're not going to really stay at the rings. And then we're going to go rings. Let me look this up. Make sure that we're doing it right. Okay, very, very high level only. So we're going to go Earth to Saturn. Then we're going to call low Saturnian orbit phase. Then we're going to go LSO to rings. And then we're going to go rings to Enceladus. And then we're going to go Enceladus to Titan. Then we're going to do Titan to Iapetus. And then we're going to do Iapetus to Earth. And let me just go ahead and check everything. Okay, so I had to clean it up a little bit. And let's see, we also got to add, there we go. So we're all set now. We're going to go Earth to low Saturnian orbit to the rings, rings to Enceladus, Enceladus to Titan, Titan to Iapetus, Iapetus to Earth. Okay, so after doing research, I was going to aim for this dark region between the A and the B ring, known as the Cassini division, but I'm a little bit concerned because I'm reading that there's material there. That sounds a little bit dangerous, so I think what we're going to try to do is just aim for shooting roughly past the F ring. I think is the safe way to do things. So here we go, Saturn ring F, and then we're going to go down here. Instead of just saying rings, F ring, to be a little bit more specific. So I don't intend to hang out there. What I want to do is basically fly by the F ring at a very close distance, is what I am trying to do. Okay, and how about that space environment that we were talking about? We're going to have to describe everything, right? So we're going to launch, so we want to take off from Earth. So I want atmospheric Earth flight. Then I want LEO, low Earth orbit operations, so that we can check things out as necessary before we go crazy and burn like crazy to go into deep space. Then we need interplanetary space operations. Okay. Then we're going to come down to Saturn and we're going to fly through the upper atmosphere. So we need a way to fly into Saturnian atmosphere. Now, Saturn isn't as crazy as Jupiter when it comes to radiation, so I'm not going to include it as its own special thing like I would for Jupiter. It's not like it doesn't exist, but I'm going to pretend that we don't need to do anything special to do this. Then we're going to take off. We're going to land. We're not going to take off from Saturn. We're going to fly around the rings, and then we're going to get into orbit around Enceladus. There's water ice plumes, but at the speeds we'll be moving and the atmospheric protection, there's nothing special that we got to do there. We're going to land on Enceladus. Then we're going to take off. And then after taking off, we're going to fly to Titan. So we need 90 Kelvin atmospheric flight capability, and we need to be able to deal with atmospheric pressures of 146 kilopascals. So that's the environment at Titan. We got to make sure that the chamber pressure of our craft is okay to work at 146 kilopascal. Titan is also the strongest gravity that we'll be under after leaving the Earth. So we need to make sure that we can land with Titan's gravity. Okay? Because if we can't land under Titan's gravity, we're going to be in big trouble. Well, I guess we just wouldn't land. We would just continue flying. And then we're going to land on Iapetus, which is the same environment, give or take, to Enceladus. That's not completely true, but it's not going to affect us. And then the rest of it retraces the steps back to Earth. So that's our space environment that I am going to note later on when we select a vessel. And now this is what I like to call the technology table. It affects what assets we have at our disposal for a given mission that we're going to fly. We can choose a hardware generation of 5, the 5th generation. You have Mercury, Gemini, Apollo, Space Shuttle, and basically what we have today. Starship could fit under this category. You need servers to plan the mission if you're going to do this, and it involves a mothership, assisted home and transfer, which means you take off, you refuel, and then you go to a mothership. You refuel on the mothership, basically. The mothership flies from A to B. Then the mothership refuels at the destination, and then you go to the surface, and then you come back and refuel again at the mothership. Then the mothership comes back to the Earth, and then you re-enter and land. Very complicated. On the other hand, we could use what might be Generation 20 in the year 2500, where there's no plan. You just AI. I want to go to Mustafar, using a technology level of Star Wars, direct hyperdrive personal space plane. Basically what the Royal Shuttle was on Naboo that Queen Amidala uses to go back and forth between Coruscant and Naboo. That would be something. It might not even be 2500. We might be talking millions of years. It's almost unknowable what kind of technology we would need. It might not even be possible to use a direct hyperdrive in something like a personal space plane. But you never know. I mean, look at your cell phone and think about how big a computer was in the 1950s. And how that compares with your cell phone. It's possible. So basically what I'm trying to say is the further back in time you fly, the harder it is to plan and the more complex the mission. The harder it is to plan a mission, though, the more exciting it is. For example, if you go with warp drive, you might be like, oh, it's Mars, warp again. Hey, it's Neptune, warp again. Ceres, look at that. Not that much fun. On the other hand, if we do the 2024 tech level, this happens.
Attention all crew, we're about to start the orbital maneuver. Please perform your pre-maneuver checklist. We need all engineers at the front deck for instructions, and also please verify that your cabin is secured before the maneuver.
So the tech level affects O2 longevities, fuel efficiencies, engine power, where you can refuel, and the feats that you can accomplish. So, which tech level am I choosing? I'm choosing the direct Hohmann spaceplane, technology level 10. This will basically balance showcasing the process of planning without going overboard and making a 100-hour video series. Okay, now it's time to ask a little bit more specific, fun questions. It's starting to get real. So now we have to really think about how are we going to accomplish this? What categories of flight do we want to be able to do? Airplane, rocket, aerobraking, gravity assists? Are we going to do that? So, what am I going to do? I said I wanted to fly in an atmosphere. So I wanted airplane independent of O2, which means we can't take a 737 and attach it to the craft, and then when we land on Titan, we deploy the 737. Because you know what's going to happen? Absolutely nothing, because Titan has no oxygen in its atmosphere. So it's basically going to not start and become a glider and then crash land. So if it doesn't explode first due to fuel freezing. So yeah, airplane independent of O2. We do not want to aerobrake, but we do want to be able to re-enter. And the reason I don't want to aerobrake is just because I don't want to be too crazy with my planning. I view aerobraking as a last contingency, right? Let's say we abort the mission. We're saying, okay, we hit the red line, we're aborting now. And we abort, and for some reason, mid-course correction maneuver goes wrong. I make some mistake, and now we're like, oh my gosh, I am actually in trouble of not being able to get back. If that happens, then what we do is we do an emergency aerobrake, which helps to recapture some of that delta V that we have planned. That's like the last ditch effort before, you know, it's lights out. We mess up the aerobrake, and that's the final ace up my sleeve. So I'm not going to plan to aerobrake. Did we consider gravity assists? Yes. Jupiter is going to be in the roughly the same location as Saturn. So it's not in a good position to do a gravity assist. So we can't do that. No gravity assist. How will you plan to take off and land? VTOL or airplane? Both, actually. On Earth, we want to take off and land normally, but every other landing, we want VTOL. And the reason we want VTOL capability is because we have no runway surface prepared. Even on Titan, because we can fly like an airplane, that doesn't mean that there's a runway for us to land on. So we need VTOL. What will we take with us? Any pop-up bases or equipment? That's a good question. Let me take a look at the list of items that we have and get back to this. Okay, so I took a look at everything that's available to us, and I'm interested in a pop-up base, a flag, and a atmospheric probe, which we can drop into Saturn. And that would actually allow us to see much deeper into the atmosphere, but only if it fits. These are all the things that I would take if I had infinite space. So we'll see. We're going to set up a base on Titan. Next is, what do you plan to deploy or jettison, and how do you expect to do that? Let's see. The only thing that we need to do is make sure that we can pack and unpack the cargo from the ship. That's fairly straightforward, so we just need a cargo bay that opens. Everything that I know of you can put things into and out to work, so we can ignore that. The next thing is the satellite, so we want to deploy the satellite. That might require an EVA, so we need space EVA, and we also want surface EVA. So we need a way to exit the craft outside of Earth's atmosphere on the surface, which means we need an airlock. Alright, and then which software are we going to use to plan the mission? I should note that for very complicated missions, which are Generation 6 or below, you would really need an enterprise solution like GMAT or STK to do this. If this series is quite successful, I might demo that in the future just to see what it's like planning a modern day mission. I am going to use my own Excel software package that I've developed, and all the calculators. That's going to be my mission planner for this mission. The accuracy that I'm accepting, let's see, I'm going to need to calculate this out. Okay, so the accuracy that I am going to accept is 4.2% error, which we will place in the RCS tanks. We'll fill the main tanks to exactly the expected volume, so we'll end up basically with zero fuel in the main tanks if we planned it right. Otherwise, if not, then we'll take some from the RCS tank. So, our mission success criteria: land. Do we need the Saturnian atmosphere? Do I want to make that a mission success criteria? I don't think I will. That's risky, so we'll consider it optional. Land Enceladus, land Titan, unpack base, land Iapetus, and return safely to Earth. Because if it matters, we could go to Cape Canaveral or Woomera or any base that has a runway that we could go to. Heck, we could even land at an international airport if we needed to. So I'm not going to specify a runway. I don't think we need to go that far. Okay, and what is the abort criteria? For me, I'm going to use that remaining 4.8% and add it to every engine firing continually, and we'll develop a line from that. If the total used fuel violates that 4% cumulative planning safety margin, the flight aborts immediately to home base using the most direct method. So let's say we are getting ready to land in Titan. We have done our re-entry, and we are beginning to get down to the surface. And during the hover phase of the flight to a soft touchdown, I find that before we begin, we have less fuel than is required by that 4% safety margin. We're going to immediately shut off the hover engines, turn on the main engines, climb up into Titan orbit, escape Titan, escape Saturn, and go directly for the Earth. That's how that works. That's it. So now we're going to look at matching an itinerary to a vessel. Okay, we're going to actually look at selecting a vessel now. So the first thing that we need to do is describe the mission in vessel terms, which means that we need to go back to the space environment notes that we talked about earlier, as well as the questions that we just answered on the previous slide, to determine or develop a description of what we want to fly. So I'm going to take a minute to do that. Okay, guys, we have our vessel selected. So I did a trade study, basically described everything that was needed in column A, and got 4 candidate ships from all of my spaceflight simulators, and basically took a look at what they can do, what they can't do. And what we found was that the Delta Glider version 3, or I guess should say Delta Glider Mark 4s, both the regular version and the scramjet version, cannot do the mission. They can't make it to Saturn, or they can, but then they have to return. They can't do anything. So the only way that this is going to work is if we either take an XR2 Ravenstar and a Delta Glider 4. The XR2 Ravenstar has a note that for 110 minutes we can fly in an atmosphere unless we deploy the radiator. The radiator requires that the dynamic pressure to be low enough, and that should be capable. I've been able to do it in Earth's atmosphere, and flying on Titan is easier than flying in the Earth's atmosphere because of the lower gravity. So we can actually get around this condition. On the other hand, the Delta Glider 4 has a maximum landing weight of 19 metric tons. And this actually did become a problem. I have it logged in my Uranus flight that seconds before touchdown, I realized, oh my gosh, I'm over maximum landing weight. So I opened up, about hovering 10 feet above the ground, I opened up the payload cargo bay and yeeted the oxygen container over the side for that final 10-meter drop, and that brought me under my landing weight of 19 metric tons. So then I did a little bit of a avoidance maneuver to avoid coming down on that oxygen container, and safely landed. It was hilarious and pretty memorable. But the issue that we're going to face is that we're going to be dealing with larger moons and more of them. So we're pretty much guaranteed to land at higher than 19 metric tons, and yeeting cargo over the side might not solve the issue. So as a result, I have decided that the XR2 Ravenstar is the ship to fly. It is the best when it comes to high weight landings in an atmosphere. The Delta Glider 4, doesn't matter how soft your touchdown is, you could be going 1 centimeter per second. If it senses a touchdown over 19 metric tons, you're done. On the other hand, the XR2 Ravenstar, the absorption is based on how quick you touch down. If you touch down at a very slow speed, 1 centimeter per second, there's virtually no maximum landing weight. I mean, there is, but you couldn't possibly load the XR2 with enough mass. On the other hand, if you tried to land at 3 meters per second, you will collapse the landing gear. So we'll just have to keep that in mind. But we are using the XR2 Ravenstar, and that completes the initial planning stages. Okay, and even though it sounds like a good thing, the initial planning stages are complete, what comes next is the grueling full mission planning. I'm probably not going to show you all of it. I might show you how to take off, fly to Saturn, land, and then take off at Enceladus, and then show you the changes that we have to make to do Titan, and then maybe return to Earth, just because there's a lot of maneuvers that are going to take place. I'm probably going to have to, no, I'm definitely going to have to expand this chart. So, until then, I've been Dr. Aeronautics, and I'm sorry, I despise ads, but I am trying to grow my channel. If you like this, then please like it on the YouTube page. Comment, subscribe. Like I said, I'm trying to grow my channel. And I'll never make people pay to view my videos. I'll see you guys next time for the full mission planning. Bye-bye.